Okay, this is combined into one chapter, so as I present this, it all falls under chapter 7 and 8. And this revolves around atomic theory. The presentation in this subject is going to be more of a historical cross-section of the development of the atomic theory. Up to this point, we have invested in talking about atoms and how to identify certain structural aspects of the atom from the periodic chart, put together molecules, learn how to name molecules, and talked about formulas, types of formulas, and then interactions of the molecules and elements by reactions, and we looked at the stoichiometry, how to do reactions, all the way up through there. At the end of thermochemistry, I blocked that section off as what I call basic concepts. And when I start the atomic theory, it'll appear that I've started all over with something entirely new in the concept of teaching chemistry, and it will look like it. But what we're essentially doing is going into the micro fine structure of atomic atoms and how it evolved to understanding its structure and how it behaves. One question I ask is, do you believe in atoms? Okay, well, the answer is, yeah, Mama said so. Okay, this kind of thing. Well, nobody's ever seen an atom. Some people claim they've seen arrays of atoms using electron microscopes, but that only shows little bumps in a picture. That's all you can really see. So how do scientists know that the atom is made of two parts, nucleus and electron cloud? And beyond that, how do they know about the electrons that reside in the various levels, rings? And then how do they know where the electrons go and come in chemical reactions? Well, this is what we're really getting into, is more of the definitive nature of the atom and its down to the core issue. That is, we're looking right down in the middle of it. How do we know it's an atom and what is the structure? Well, when Dalton came out with the first atomic theory, well, let's back up even to 600 BC. First atomic theory, Democritus. I-E-S, I guess, R-I-T-E-S, Democritus. I don't know. What he did is he said, if you take a particle and you split it in half, and then you take one of those halves and split it in half, and then you take one of those halves and then you split it in half, and one of those halves and you split it in half, etc. Eventually you will come to a particle you cannot break down. The indivisible particle. And in Greek, this is called the atomos particle. And more trivia than anything else, I think you can see that's the origin of the term as it applies to particles of matter. It comes from the first atomic theory. Now, it was postulated strictly on a philosophical foundation, had no scientific basis. But the modern atomic theory is based upon the postulates of Dalton's atomic model. In reality, he did not propose or describe the actual microstructure of the atom. He didn't know what it looked like. He just said, well, carbon atoms, there's a carbon atom, and here's an oxygen atom, and here is a nitrogen atom, and here is a chlorine atom, like, you know, and just went on, made up bunch of symbologies, which had no real relevance in terms of structure. But he is credited with the first atomic theory in that the conclusions and postulates he presents are based upon experimental scientific evidence. And so the Dalton postulates are as follows. And I think I've mentioned these before if I hadn't anyway. The first one is all matter is made up of particles. Okay, I think this is also part of the kinetic theory. Made up of particles. Particles interact by attraction, repulsion. All particles are in constant motion. The velocity of particles is directly proportional to its kinetic energy content. In other words, you heat a particle, it's going to go faster. Cool it, it goes slower. And finally, it is assumed that all particle collisions in a quantity of particles is perfectly elastic. That is, the collisions do not have an energy change. In reality, they do. But particles absorb electromagnetic light and return to high energy after they lose energy in collisions, but that's not taken into account. It just simply says at a certain set of conditions, all particles bounce into one another, but they don't energy change. That is, collisions are perfectly elastic. And I use the buzzword considered to be, and what you translate that is, well, actually they're not, but it helps in this situation. Considered to be perfectly elastic. So that begins the chase for the atomic concept and establishes the idea, well, what does the atom look like? Well, there are four historical models of the atom that evolved after this. Those include as follows: the models of the atom. Yeah. There are four models, historical models of the atom, and they are the Thomson, raisin pudding, raisin pudding model. There's the Rutherford shell model. There's the Bohr, B-O-H-R, concentric ring model. And the Schrodinger quantum model. That's the one we subscribe to on today's atomic theory. And there's some fascinating science in all of these. And they go online, and I publish some of these. The Search for the Atom is in special videos. If you go down to the bottom and look in the online, there's one on there, the Miracle of Light, or something like that. And then they talk about the history of the development of the atomic theory. And it's very, very good. You just get your box of popcorn and lean back and watch it. And it is very informative. And I encourage you to do so like that. Well, as I go through these and tell you the postulates and the background of each one, you'll find as I get from top to bottom, it gets more complex. So we'll only take a few minutes to explain the Thomson, and then we'll go on to the Rutherford, and then we'll take a little longer to do the Rutherford, and then take a whole lot longer to do the Bohr model. And then the rest of the book is the Schrodinger model. So let's start out with the don't get vertigo looking at my titles there. The Thomson model there is based upon opposites attract concept. Science in general, what is known is the electron is known to be negative, and they knew about the proton, which is known to be positive. Well, Thomson took that basic idea and said, okay, the atom in 3 dimensions is a spherical entity and is positively charged. The protons make up a positively charged sphere, and embedded in those in there are the electrons. I can't use green because it never shows up. Let's see if I can find one that will. Maybe red will come. Could you close that door for me? Thank you. Okay, so we'll put some electrons suspended in the sphere. So you're looking at some kind of hazy sphere you visualize, and the electrons are suspended in that positive environment like raisins in a gelatin pudding, and hence the idea of the raisin pudding model. So well, that theory crashed real fast, okay? And when Rutherford did his experiments, he came up with the idea of the two-part atom. Okay, so now we look at the Rutherford shell model. Rutherford envisioned the atom as two parts, a dense nucleus having a positive charge surrounded by electrons, certainly having a negative charge. Neutrons hadn't entered into the picture as yet in this concept. So what he envisioned was a spherical entity like the Thomson model, but inside was the nucleus, very dense nucleus with plus charge and a hazy spherical cloud of electrons around it. Now, there was no definitive listing as to the organization of the electron structure. In other words, he didn't say it had 2 in the first energy level, 8 in the second, and so forth like that. He didn't know about the 2n squared thing at this time. Bohr came up with that. But at any rate, this is what he envisioned. Now, how did he get there? Okay, his conclusions for experimental based upon the classic gold foil experiment. Won him the Nobel Prize and so forth and so on. And what he did is he set up a lead block, bored a hole in it, and inside that block he placed a radioactive substance that was an alpha generator. And maybe you've heard of the types of radiation, alpha, beta, gamma, and so forth. Alpha particles are actually helium nuclei without the electrons running out. And is usually identified with a little alpha. Now, he had a chamber that was coated with photosensitive material in which he shot there's make this a little purple as the photosensitive material, and he directed his alpha particles at a suspended gold foil leaf, and he'd hammered it down to, what he tried to do is get it down to 1 atom size. Now, what he observed was that most of the beams just went straight through and hit on the back of the exposed disc. This was 99% plus. All particles just went right through and didn't touch anything. He saw some of them deflect, a small quantity deflect at obtuse angles like that. Smaller, and much smaller than 1%. And every very, very rare occasion, he observed particles that were reflected right back at the source. And the fact that most of them went through, he claimed, and one of his postulates is the atom is mostly space. Okay, and it consists of that very, very dense core structure, and the inherent nature of atoms were electron cloud close, but not nuclear close. And the dots in the center represent nuclei. But when he sent the alpha particles at most of them just passed right through and hit the photosynthesis back in the back. That's where the majority. However, if a particle came close to a nucleus, it was deflected and repelled. The alpha particle, being a helium nucleus, has a +2 oxidation state. Okay, so you're bringing a positive particle close to something that's reflecting it. Well, opposites attract. Opposites attract and likes repel. So he assumed 2 like charges. Okay, the nucleus is positive now. And then he had some that would actually bounce off the nuclei and come straight back to the source. Now, from this work, he was able to construct a model of the atom in terms of linear dimensions, mass relationships, and volume relationships. which is the topic of the problems that I want you to see. It was calculated by Rutherford that the diameter average of an average atom was approximately 10 to the minus 8 of a centimeter, okay, based on his Guilfoyle data. The diameter of the nucleus average was approximately 10 to the minus 13th of a centimeter. So what we're asking you is how many nuclei does it take to go all the way across the average atom? So we take an average atom that has a diameter, which would be 2 times the, well, no, it's diameter, which would be 10 to the minus 8th across here, and then you have a nucleus that has a diameter of 10 to the minus 13th of a centimeter. Well, how many 10 to the minus 13s, listen to me, how many 10 to the minus 13s will go into a 10 to the minus 8? See what I'm telling you? How many little nuclei will it take to go across the diameter? Well, if we take 10 to the minus 8 divided by 10 to the minus 13, we get 100,000. Okay? So the conclusion is one atomic diameter equals 100,000 nuclear diameters. It takes 100,000 nuclei, 10 to the 5th nuclei, to go across, lined up, side by side, to go across atom. Well, if we assume, hypothetically, the diameter of a nucleus is equal to 1 centimeter, about the size of marble. Okay, where is the outer edge of the atom? Well, it takes 100,000 of these to make a diameter. Then we divide by 2 and we'll have the radius, and so we'll know where the electron is. So the atomic diameter is equal to 1 centimeter, and you got to have 100,000, 10 to the 5th. We have 1 times 10 to the 5th centimeters. Well, that doesn't mean anything to me either. Okay, so let's convert that into something we can, relate to. How about yards? And then we can say football fields and stuff like that. Okay, so 1 times 10 to the minus 5 centimeters, this is the identity, times 10 to the minus 5 centimeters. We want to get rid of centimeters. We want to go to inches, and then we go from inches, and we can go to yards. How about that? Okay. And so 2.54 is an inch, and 36 inches in 1 yard. And so our diameter in centimeters Okay, the radius is equal to, of course, 1093 over 2 yards from the center. So that's 546. Well, we'll just round that off to 550 yards. So we're talking about 5.5 football fields from the point of the nucleus, which is the size of a marble. So 5 football. Well, you can convert this to miles, And if you convert this to miles, it's about 0.6 miles, about a half a mile. So here's your marble, and half a mile away is the edge of our atom, outer ring of our atom. And that kind of gives you a cross-section of, well, it's mostly space. And so that is very legitimate. So what you should take away from you here is, if you have to describe the atom, what you want to remember is 1 atomic diameter is equal to 100,000 nuclear diameters. Now that's simple to remember, or 10 to the 5th nuclei. Choose a nuclear diameter, 1 millimeter, size of a BB, or the size of a baseball, 3 inches, or a basketball, where you can convert that size and dimension to where's the electron on the outer edge of the atom. So that's one classic. That's a classic outcome. Okay, so these are the nucleus, the atom, big part, that's the total. And then we want the percentage weight for the nucleus, as nuclear weight divided by the atom times 100. Then we'll take the electron weight divided by the atom weight times 100, and we'll get the weight percent contribution of the nucleus. Weight percent of nucleus is equal to 6.696 times 10 to the minus 24 divided by 6.6978 times 10 to the minus 24, and that's times 100%. The weight percent of the electron cloud is 1.82 times 10 to the minus 27 divided by 6.6978 times 10 to the minus 24, also times 100%. Okay, let me I'll move this over here. Okay, you better easy to see it. The nucleus obviously contributes 99.973% of the weight. It is all weighed by the nucleus and all compact down into 100,000 of them to go across the nucleus. So in essence, you can say the nucleus is 99.9% of the mass of a given atom, and the electron represents almost nothing, and the total contribution to the mass of the atom. So up for you. One atomic volume is this number, and one nuclear volume, I went ahead and ran it out using the standard spherical volume equation like this. So the number of nuclei per atomic volume would be 5.23, I'll drop this other 3, times 10 to the minus 25 divided by 5.233, I kind of made it come out like that, times 10 to the minus 40. Okay, well, of course, these drop out, so it's really a differential between 40 and 25, so 10 to the 40 minus 25 nuclei per atomic volume. And that kind of works out to be 10 to the 15th nuclei per atomic volume. That's 1 and 15 zeros. Well, what size number that is, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 nuclei. And it's like a basketball, punch a hole and fill it up with BBs. But for an atom volume, it takes, I don't know, it looks like 1,000 million million. 1,000 million million. So what am I trying to teach you here, and what I want you to take away with you is a linear dimensions, 100,000 nuclei equal 1 atomic diameter. Mass dimensions, nucleus and atom. The nucleus equals 99.973% weight contribution of the atom, and the electron cloud is equal to 0.027% weight of the mass of the atom. So these are classic numbers that you use for whatever reason you have to find yourself describing what the atom looks like. And volume relationships. 1 atomic volume equals 10 to the 15th nuclear volumes. So that's the purpose of the extent of what I wanted to go through in the Rutherford model. Our next lecture will focus on the Bohr model. And here he used these bright line spectrum. That's where Niels Bohr used hydrogen spectrum, which is right here. There's 4 lines of hydrogen spectrum to draw the conclusion of the concentric ring model. This is when we still use in a lot of cases where you have a nucleus and you draw rings around it and say, okay, it's got many electrons, there's a valence, and so forth and so on. But that's where it comes from, and I want to be aware of how he came to the conclusions, well, as a concentric ring model. And then we'll move on to the Schrodinger model and then so forth and so on.